Okay, so yes, this discussion is going to be on your exam, the material from here. So the membrane forms a selective barrier for the passage of molecules. Explain briefly. Okay, so we have the membrane here. What can pass through? Anything that is small, anything that is uncharged, and anything that is hydrophobic. So that kind of stuff can just pass freely. You do not need a transporter. You don't need anything. And then they give you two molecules. Now that you know the rules, small, uncharged, and hydrophobic, they give you two molecules. And they tell you which one is more permeable. Permeable is just the word that they're using to cross the membrane. Which one can cross the membrane faster, better, more efficiently? That's what permeability means. So here they gave us indole and they gave us tryptophan. So we know that tryptophan is an amino acid. And then they told us, oh, you have a pH of 7. Okay, so we know that at pH 7, the carboxylic acid group of tryptophan has already donated its protons. So it has a negative charge, right? Because its pKa value was like 2.34 or something. Okay, and then the amino group, the NH3 plus, it hasn't donated its proton because its pKa value was like 9 point something. And we're only at 7. So it has a positive charge. So this amino acid tryptophan has 2 charges. So what does that mean about its permeability? It's not really going to be able to cross the membrane, right? Because only uncharged stuff can cross. But if we look at indole, it's got 2 little cyclic structures and it has an NH. Now, this NH for indole does not donate its proton, no matter the pH. So it is not ionizable. It won't have a charge. It's going to stay like this. So indole is small, it is uncharged, and it's mainly carbons and hydrogens, so it's going to be hydrophobic. So that is why the indole has a higher permeability than tryptophan. Does anyone have any questions, or will you be able to answer if you get something like this on the test? You will be able to? Okay. Okay, so now we're going to talk about channels versus transporters. So there's different types of channels. Look through your notes, learn the different types. And transporters, there's different types, learn the different types. I'm just going to cover basic definition stuff. This will help you eliminate a few of the wrong choices whenever they give you a question like this. So channels, they have 1 gate. Transporters have 2 gates. So whatever's going through a channel, it moves fast at the rate of diffusion. That's super fast. Transporters, whatever's moving through a transporter moves really slow. Why? Because there are 2 doors. So if I'm going to be the molecule that is going to be moved across, I have to open the door, come on in, close the door, and only when that door is closed can I open the next door. Come out, close it. And that's why it's slow. I used to feed tigers and lions and stuff, and that was exactly the mechanism. I had to open one door, lock myself in, make sure in case the tiger gets out, it only gets me, like not the rest of society. Then open the other door and then close, you know what I mean? So it's the same as a transporter. That's why it's slow. Channel, down the electrochemical gradient. So when you open the 1 gate for a channel, if there's a million sodiums over there and only 1 over there, they're just going to move down their electrochemical gradient until we have 500,000 over here and 500,000 over there. That's a channel. It wants to stabilize. So things move down their electrochemical gradient. For transporters, they move against their electrochemical gradient. So for a transporter, if I had 1 million sodiums over there and only 1 over there, that 1 sodium will move across against the gradient. Channel can't be saturated. It means it can't get full. You just open the door and then everyone goes through. It can't get saturated. The transporter can. Okay, so this is a really popular question for like quizzes and exams. You have the potassium channel. And what happens is you have a little tiny potassium here. And potassium is hydrated, okay? It is hydrated. What does that mean? A lot of students are afraid of that term. All it means is that there's water molecules around it. So you have potassium with 4 little water molecules. Because potassium has a positive charge, the oxygens are the ones that are going to be next to the potassium. And the hydrogens will be on the outside. So this is hydrated potassium. Okay. Over here we have a selectivity filter. A selectivity filter. So what exists in this selectivity filter is carbonyl oxygens. So they belong to like other amino acids, right? But here we only have the carbonyl sticking out. So the purpose of that is because when the potassium starts getting closer, the slight negative charge on the oxygen is going to stabilize this potassium. So it's going to have the same effect as the hydrated potassium. And so the little water molecules will fall up. Okay, see that? The little water molecules just fall off. And then potassium is the perfect size to make those interactions with a positive charge and then partial negative charges on the oxygen. They stabilize it all the way through. So that's how this works. Now, a question that they might want to ask you on an exam or a quiz is if potassium and sodium, they're really close to each other on the periodic table. They have a lot of the same characteristics. They both have a +1 charge. So how come sodium can't pass through this filter? So the reason is that the diameter is too small. Potassium is the perfect size for these interactions. Potassium is too small. So the negative charge on the oxygen is trying to reach out and stabilize it. It can't, it's too small. And that's the answer. Does it make sense? Yeah. Okay. Types of transports. We have uniport. That means one little guy just moves across the channel at the same time. At a time. And then we have co-transport. For co-transport, we've got 2 different types. We're looking at this. So for co-transport, we've got symport. Now you have to absolutely have all of these terminologies memorized. Symport means that both items are moving across in the same direction. Sometimes you'll get a paragraph and the only clue that they'll give you is symport, and you have to get to the right answer based on symport. So that just means they're both moving in the same direction. Antiport means they're moving in the opposite direction. So symport and antiport are methods of co-transport, where 2 items move through the same channel at the same time. All right. So it's important for you to know that before we get to this other question. Now, this question has been on exams over and over again, and students always, like most students, will lose all their points here. So pay extra attention to this. It's actually really easy, but it's also very easy to make a mistake. I'm going to read the question to you. It's usually a paragraph. Okay. E. coli cells. Let me see here. 5. Okay. Okay. E. coli cells transport xylose across the cell membrane via a symport system. What does symport mean? Same direction. So this was important. If we didn't know that, we would have failed this question, most likely. So symport means same direction. So when you get to the exam, don't be afraid of these terms, just write down what they mean. So that uses the free energy of a proton gradient. So anytime you have a gradient, that gradient is going to produce some free energy that now xylose can use that free energy to hitch a ride. It's like if I pay for a taxi, but someone else is hanging out and they're going in the same direction, just hitch a ride with me for free, right? So that's what's happening here. So they're saying that you have a proton gradient. So I always make a note of that. All right. Okay. So all that's left to determine is what direction things are moving in. So they're going to give us a clue. And this is where students make the mistake. The intracellular pH is higher than the extracellular pH. That's it. That's your clue. You have to be able to answer the whole question based on that. So can you guys remind me, what is a high pH? Because they said inside the cell, you have a higher pH. What is that? Acidic or basic? Basic. What about low pH? Okay. Who is the proton donor? The proton donor, the acid. So if you're going to be donating protons, what does that mean? How many protons do you have? You have a lot, right? You have a lot of protons. Protons have a positive charge. You can draw the little hydrogens, but just for faster. Okay? And now bases, what do? They accept protons, right? So what does that mean? Do they have a lot of protons or a little bit? A little bit. You just draw that out. So students are moving so fast through the test that when they see high pH, they just drew in a bunch of protons, a lot of protons. Low pH, so they drew a little bit of protons. Do you see how they had this completely backwards and it cost them all their points? Don't do that. Label. Work slowly and work correctly, okay? So now, there's a proton gradient. What does this mean and which direction is the proton going to go? This way. And because this is symport, what does that tell us about the direction of xylose? Great. Yeah, and they even ask you to draw a diagram. So one more thing that we should know about xylose is it required energy to move across. What does that mean? Is there going to be more xylose here or here? Is it going down its concentration gradient or against? It's okay, down or against? Against, yes. So that means that there should be a lot more xylose in here. And let's just say that there was 2 xylose over here. So if xylose was moving down its concentration gradient, it would have just moved that way. But it's requiring that energy from the proton gradient, so it's going to move against its concentration gradient. So it's mainly terminology that you have to know, but then you can break down the problem and it's not too bad. All right, now we're going to talk about valinomycin. Valinomycin is an antibiotic, okay? It's a tiny little molecule, and then inside there's a little pore. So this is valinomycin. It's an is it an yeah, it's an antibiotic, so it kills bacteria. Antibiotic. You're supposed to know the mechanism by which it kills the bacteria. So on the outside of valinomycin has nonpolar hydrophobic groups. So all of this is nonpolar, so that's fantastic because it is small, it is not charged, and it is hydrophobic. So what does that mean about its permeability through the plasma membrane? It can cross, right? Easily. Valinomycin is a small, nonpolar molecule on the outside, so it can cross through the plasma membrane whenever it feels like it. Now, on the inside, there's a pore. This pore is surrounded by oxygens. So you have a, what do they call it? They call it a hydrophilic cavity. Okay. Now, here's a cell. Just imagine this guy is way smaller. Okay. So that's the cell, the bacterial cell. Okay. And remember that cells, they spend energy to create a transmembrane potential. And it's usually like -70, right? Or like -65. Like they do that on purpose so that things can function. If this transmembrane potential is ever 0, the cell will die. Okay? So valinomycin, what it does is it carries potassium down its electrochemical gradient. So it will cause this to go to 0. It'll remove that electrochemical potential. It'll neutralize it. It'll make it 0. And that is how it kills bacterial cells. So for example, if the cell's working really hard to get rid of the potassium, well, valinomycin is just going to go grab the potassium and bring it inside. And then it's going to go grab another one and bring it inside. And then it's going to go grab another one and bring it inside until the cell dies. And that membrane potential is neutralized. Does that make sense? Kind of, yeah. Just review it a little bit. Okay. I think there's 2 math problems, like a simple one. Is there? Oh, we'll just, yeah, it's just a one big problem. Okay. So now we're going to go ahead and talk about energetics. Oh, no, we already did. Yeah, energetics. Okay, number 6. Okay, so this is the hardest part for students. So delta GT, that is the free energy of transport. Transport. Because here we're talking about transporting molecules across the membrane. So free energy of transport. So there are two things that are associated with transport, two ideas. There's a chemical gradient. So this is a chemical gradient. Now, sometimes they'll ask you to do the math. And they'll ask you just for the free energy of transport. Sometimes they'll ask you for only the chemical gradient portion. Sometimes they'll ask you for the electrical gradient portion. That's this guy. So pay attention to what they're asking you. Because if you know how to do all of this, then you don't want to lose points for no reason. Chemical gradient portion, electrical gradient portion. Now, you have to have memorized what each of these are, and then you will be able to answer any question that they ask you. Okay. So if the atom or molecule that you are transporting does not have a charge, you only have to do the chemical gradient math. If the molecule you're transporting does not have a charge, you only have to do the chemical gradient math. But here, they're telling us, oh, you're going to transport sodium. Sodium has a charge. So that automatically tells us we are going to need both. We're going to need to add both. And that's going to give us our free energy of transport. Okay. Yeah. Today we're going to memorize what each of these are. So, what is R? What is it? Universal gas constant. Yes. And you have to know the units. Okay? So it's 8.315 joules. You have to know that it's joules, not kilojoules, per Kelvin mole. So R, that's easy. It's always going to be the universal gas constant. Now, what is T? Yeah, so it's going to be absolute temperature in Kelvin. In Kelvin. Okay, easy. So they usually give you 37 degrees Celsius. You have to know that 37 degrees Celsius is equal to 310 Kelvin. So just like to memorize that. That's usually what they give. Okay. So this is just ln of C2 over C1. So what is C2 and what is C1? So this is really easy. Here we're moving sodium. So for example, if we're moving sodium outside of the cell, then our C2 would be the final destination. If we're moving if we're moving sodium into the cell, then whatever concentration is here, that would be our final destination. So C2 is always final destination over initial destination. Easy so far? Yeah. So R, universal gas constant, 8.315 joules per Kelvin mole. T, absolute temperature in Kelvin. C2 over C1, final destination concentration over initial destination concentration. Okay, and that's all you need for your chemical gradient. So if your molecule is uncharged, this is all you need, and you'll get the right answer. But we have sodium. So we need to know all that stuff over there. So what is Z? So Z is really easy. It's literally just the charge. So our sodium has a +1. So Z is just 1. Easy, right? Okay. So F is Faraday's constant. That one is hard, so I think if anything, they'll give it to you. They should hopefully give that to you. I don't think anyone would expect you to memorize that. Okay, but it is 96,500 joules per volt. So notice that R and the Faraday's constant is in joules. Okay, your final answer for delta GT is going to be in kilojoules. So just keep that in mind. So the very last step is going to be to convert to kilojoules. All right, we're almost done. Last thing, delta psi. Delta psi is equal to V. It's the transmembrane electrical potential, and it has to be in volts. It has to be in volts. They will not give you this number in volts. When they give you a paragraph, it won't be in volts. It'll be in millivolts. You need to convert that before you plug it into the formula. So I'm going to put a little star here so you can. They will not give you that number in volts. I mean, they might this semester because they're doing things differently, but I've never seen it. They always give it to you in millivolts, even in this example problem, and then you have to convert it before you plug it in. All right, so we're ready to plug it in and give you like a full example. And then on the exam review, there's another full example, and I walk you through that as well. So hopefully that will help. Okay. So assuming a membrane potential of -70 millivolts, so I'm going to start writing mine. That's -70 millivolts. That goes right here. So -70 millivolts. Oh, there's a rule that affects it. When a positive charge is moving out of the cell, this value will be positive. So the rule, I'll just write it. Rule. So when a positive charge moves out of cell, the transmembrane electrical potential is equal to positive in the formula. So even though it's negative for our formula, we're going to leave it as positive. But the first thing we have to do is convert it to volts. So milli is 10 to the -3, and we just want volts. So all we have to do is move it 3 decimal places this way. 1, 2, 3. So our new answer is 0.070 volts. So now we can go ahead and plug that in. I'm going to plug it in one. So here we go. I always write parentheses around my numbers so that it's easier not to make a mistake. Try to be as clean and organized as possible. You don't want to have to erase and then redo things when you're rushing. Okay. There it is. Let's go ahead and fill that in. 96,500. 96,500 joules per volt. Okay. Now Z. What was our Z? 1. Because our sodium that we're moving has a +1 charge. Okay, so we're done with our electrical gradient stuff. That was easy, right? Okay, so now we're going to go ahead and do our chemical gradient stuff. We can start with R. So R is just the universal gas constant, 8.315 joules per Kelvin mole. Okay, what was our temperature? 37 degrees Celsius. So we know that it has to be in Kelvin, so we do 310. If we put 37 Celsius, the answer is going to be wrong. So I'm going to put a star next to that one too, so you can make sure to convert. Because for some reason, they always give it to you in Celsius. I don't know why. I think they want to make sure that you know that like it's that extra step that you have. Okay. So the last thing we have to plug in is the ln of concentration 2 over concentration 1. So ln of, so here it says a concentration of sodium inside the cell of 12 millimolars and 145 outside. So where did I draw mine? So 12 millimolar inside, 145 millimolar outside. I recommend that you always draw. And then let's see, what are they going to say? In which direction will sodium move spontaneously? According to its electrochemical gradient, in which direction will sodium move spontaneously? So they're going to ask us several questions. So is it going to move this way or that way? Spontaneously. This way, right? Yeah. So spontaneously means with like no energy. So that would just be down its concentration gradient. So we just answered the first question. Okay, it would be into the cell. The next question. Under the same conditions, calculate the total free energy change for transporting 1 mole of sodium out of the cell at 37 degrees Celsius. So now for the calculations, they want us to go against the electrochemical gradient, right? So that's why it's going to cost energy, and that's why we have to do math.
Is that also why it's positive?
Yeah, I think so.
Okay.
Yeah. Okay, so now we know what is our final destination here. Huh? This guy? Yeah, because we're going from inside to outside. So the outside would be our final destination. So that's our C2, 145. And here you don't need units, it's just 145. And then the inside is 12. So the units are canceling out, that's why. Okay, so then that's it. You just do the math. So this is where you have to pay extra attention because they can tell you what is the, so here they tell us what is the change in free energy due to each, the chemical gradient and the electrical potential. So they're expecting you to give them two answers. This one and this one separate. Sometimes they'll just ask you what is the total energy of transport to transport 1 mole of whatever, and at that point you have to add the two. You see the little plus sign, right? So pay attention to what they're asking. But basically here, when you do the math, this is 6,423 joules per mole, and this is the chemical plus, and then here's 6,755 joules per mole. So the total free energy for both the chemical and the electrical gradients is equal to like 13,000 something. Joules per mole. Okay, but remember, when they ask you for the delta GT, it's in kilojoules. So you just move it over 3 decimal points and it gives you 13.2. Kilojoules. There's more numbers over here, but I didn't, they skipped that calculation and I didn't do it here. Kilojoules per mole. Is that easy? You'll be able to do it?
If it ends up transporting 2 moles of NA out, would it change any part of the math or not?
I've never seen them give you that, but basically it would just cost, it would be this times 2. Because to transport 1 mole, it costs 13.2 kilojoules per mole. So if you had 2 moles, you would just do times 2 moles. And then you would cancel out the moles and you would just do this times this and it would equal, what, 26.4 kilojoules. Good question, yeah. Okay. So the next question is a typo, has a typo, but it says how many moles of ATP? So how many moles of ATP? How many moles of ATP would be hydrolyzed? So students are afraid of this word too. So ATP being hydrolyzed, remember you have a phosphate, 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 right? That's ATP. So this third bond has the most energy. When you break it, you get to use all that energy. And they're telling us here that it's 58 kilojoules. So when you break this bond, you get to use 58 kilojoules. Now, you break a water molecule is the one that comes in and breaks the bond. So they're saying ATP hydrolysis. Hydro means water. Lysis means break. So you're breaking that bond with water. That's all that means, ATP hydrolysis. And then we get to use 58 kilojoules. So they're saying how many moles of ATP would have to be hydrolyzed to provide the energy necessary to transport 1 mole of sodium out of the cell. So we just figured out that it costs 13.2 kilojoules to transport 1 mole. And we know that it costs that we receive 58 kilojoules for 1 ATP hydrolysis. So do we have enough for a mole? We do. We actually have left over. We probably have enough for like 2, 3 moles of sodium, right? What's 13.2 times 4? I didn't put my calculator. So you might be able to transfer like 4 molecules of sodium out of the cell with 1 ATP being hydrolyzed. Does that make sense? But you still have to answer the question mathematically. They're asking you how many moles of ATP. So we know we don't even need 1 full mole. So we already know that it's going to be like a fraction of a mole. So all you do is you divide by 58 kilojoules. The kilojoules will cancel out. Your answer will be 0.23 moles of ATP. So you didn't even need a quarter of 1 ATP mole. So that means that you could transport 4 sodium ions out of the cell against its concentration gradient.
So we just ignored them.
I would. So I had that question yesterday, and I think the reason is because this is a mold, and you can't have negative moles of anything. So I think that's why. Yeah, they don't explain like why here in the key, but. Okay, so do you guys think you can do this on the test? Yeah, okay, good. And then C, they always ask about different types of ATP aces. I know we have like P-type ATP aces, and then there's like another type, and I think we cover both of them on the exam review, but definitely review the notes for those. It says many pumps are members of the P-type ATPases. If you discovered a new enzyme with similar function, what reaction intermediate would help convince you that your enzyme was a member of this family? So P-type ATPases are reversibly phosphorylated. So that just means that if they give you like a picture and then they ask you, is this a P-type ATPase? Or they give you like A, B, C, D, E, and you want to answer that it's a P-type, what you would see is like step 1 would look something like this. And then step 2 would look So step one, there's nothing phosphorylated. Step two would be phosphorylated. And step three is again not phosphorylated. So this was reversibly phosphorylated. So it was reversible because you can add the phosphate and you can also remove it. For some enzymes, it's not reversible. So that's how you can tell that this is a P-type. ATPase. Okay, I think we covered like the whole worksheet, actually. Which one? Oh, number 3. Okay, what is the difference between passive, active, and active transport? Provide an example of a transport protein involved in the passive transport of potassium and one protein involved in the active transport of potassium. So again, definitions. Know your definitions, and then they want you to provide examples from lecture. Also explain for each of your examples if the transport is uniport, symport, or antiport. What would happen to the electrochemical gradient if potassium if valinomycin is added to a cell? So we covered that part. All right, passive transport allows the favorable movement of molecules down their electrochemical gradient. So kind of like the proton gradient, that's passive transport. Whereas active transport requires a form of energy to move molecules against their electrochemical gradient. For passive transport, you have potassium channels. So for channels, as an example, we have potassium. We have potassium channels. And we see that that's fast. There's only one gate. It goes down their electrochemical gradient, and you can't saturate. So there's channels for potassium, and that's passive transport. Okay, and those are uniporters. We saw that uniport is just symport, or uniport just goes in one way, one direction, one item. And it goes out of the cell. All right, and then we have active transport and that's the sodium potassium pump. So I'll do the notes. So here's active transport. We just covered passive. Passive required a channel. It was uniport, and potassium goes out of the cell, down its electrochemical gradient. Active will be against. And then the example is a sodium potassium pump. So a pump is a transporter. It has 2 gates, it's slow, it's against the gradient, and it can be saturated. And this is an antiporter. What does antiporter mean? Yeah, so antiport is a form of co-transport, and one item goes in one direction and the other guy goes in the other direction. So that is a sodium potassium pump. It maintains the relative concentrations of sodium and potassium across the membrane. It uses ATP to move sodium out of the cell and potassium into the cell. So this pump uses ATP. And that makes sense because we said it's going against the gradient, and it moves sodium out. So it takes sodium outside. And then it brings potassium inside. So that's active transport, passive transport. Channel versus pump. No energy required, ATP required. Down its electrochemical gradient against the electrochemical gradient. So it's all definitions. And that's it. We have 5 minutes left. Does anyone have any questions? If you don't, you're free to go.